This meeting is being recorded.
Hello, everyone. Welcome back to another edition of zkStudyClub. Today, we're very excited to welcome Liam Eagen from Blockstream Research. He's going to be presenting some new work, some joint work that he's done with Ariel Gabizon on cqlin. So with that, over to you, Liam.
Hi. So cqlin is a new protocol for Lynn check in linear time in the size of the witness vector. So I guess I'll just get right into it. Motivation. So Lynn check, many people are probably familiar. You want to check that a vector satisfies a system of linear constraints. Very common sort of sub-problem in snarks. And so many approaches to this, for example, like Marlin, take time linear in the sparsity of the matrix, right? So the linear constraints that you want to satisfy, prover time depends on how many entries of the matrix are not zero. We would like, to have prover time depend only on the dimension of the vector rather than the number of non-zero entries. Because if the matrix is dense, then the number of non-zero entries will be quadratic in the dimension of the vector. An example of where this is useful would be in zkML, where you have a lot of dense matrices that you want to multiply by vectors. This problem sort of implicit in earlier work, the GKMMM paper, which is protocol for rank 1 constraint system. But if you just sort of consider the matrix part, the linear part rather, you get an O of n Lynn check protocol in the dimension of the vector. But it has a trusted setup that depends on the size of the matrix, and it has cubic setup time. So our work, Ariel, my work, does not depend on the size of the matrix for the trusted setup and has a quadratic setup time. So just some background on the techniques that we used for this. Ariel went on the Zero Knowledge podcast and gave a talk at the ZK Summit about this trilogy of snark protocols. And so this work, cqlin, would be kind of in the third part of his trilogy. So the first phase is terminated with, say, Groth 16, where you can use pairings to get very efficient verifiers and provers without using the PCP theorem, but you need a trusted setup per circuit. Then there was a second kind of wave of snark protocols like Planck and Marlin, and these use polynomial commitment schemes. And the advantage of this is that you kind of abstract the pairing away and sort of put it inside of the polynomial commitment scheme. And as a result of only using polynomial commitment schemes, you only need a single trusted setup for any circuit of at most a certain size.
Liam, real quick, there's a question in the chat from Dara, which is, are we generally assuming square matrices? I'm assuming referring to the prior slide. Are we assuming square matrices without loss of generality?
Yes. Throughout the slides and in the paper, we assume square matrices, but that's mostly just like a simplifying assumption. It is true that you could put a rectangular matrix inside of a square matrix, but you could also modify the protocol to handle rectangular matrices directly. But yes,
okay, thank you.
So polynomial commitment schemes, yep. And then the third kind of chapter of the snark trilogy breaks the abstraction, right? So we abstracted the pairing into the polynomial commitment scheme, and then you break the abstraction and revisit pairings directly. So the sort of classic example beginning this chapter would be calc, where you can use the pairing to do really efficient lookup arguments. And then there was a sequence of lookup argument papers that I think terminated in CQ, which was kind of the predecessor work for cqlin, which I guess makes sense with the name. Yeah. So what other applications benefit from breaking this abstraction and using pairings for more than just polynomial commitment schemes with preprocessing cqlin? So preliminaries, I'll go through this kind of fast. I wasn't sure how much background to include in the slides, but so we cqlin as well as CQ use KZG commitments. They don't work with other kinds of polynomial commitments. So we use the bracket notation to commit to the polynomial f. And so KZG commitments allow you to prove that f evaluated at a equals b by proving knowledge of this q, which if f of a equals b is a polynomial. Otherwise, it would be a rational function. And so you can generalize this to proving f and g agree at multiple points if this q is also a polynomial. More preliminaries, omega, root of unity, Lagrange polynomials. They're 0 everywhere except for when I and j are the same. So they're kind of like, the unit vectors or identity matrix columns. We can encode a vector as a polynomial pointwise by constructing a polynomial so that each root of unity to an ith power maps to the ith component of the vector. And this is equivalent to writing the polynomial as a linear combination of Lagrange polynomials. And then this is just also a useful technique that we will use for univariate sum check. So if you have your polynomial and you want to sum its values at the roots of unity, then it's sufficient to evaluate it at 0 if its degree is less than n. So sparse commitments. So our goal, remember, is to get a linear time prover in the dimension of the vector, but the matrix itself will have, in general, n squared entries. And so we're interested in sort of working with commitments to larger numbers of values than the prover has time to sort of consider on their own. And so in general, we'll talk about like a sparse commitment, right? So you have a polynomial which has degree d. And in general, if you want to commit to the polynomial, you have to do d scalar multiplications, say, right? You have to commit to its coefficients or something like this. But sometimes we can have a polynomial of degree d that can be written as a linear combination of a smaller number of polynomials, bi. So there's n bi, and that's less than d. And so p can be a linear combination of these b polynomials. And yeah, the values f sub I are only non-zero very infrequently relative to the degree of the polynomial. And the point of this is that we can commit to p, we can construct a commitment to p in O of k time given pre-computed commitments to the basis polynomials. So k much smaller than d, and we can construct a commitment to p much faster than if we were to, say, compute the coefficients of p as a degree d polynomial and commit to those.
Does this assume that you're representing the polynomials in Lagrange basis?
So we will later, but it actually works for any bi. Bi
Okay.
could be powers. They will typically be Lagrange, but yeah, they could be anything. That bullet point is missing the f's multiplying the b bracket, but yeah. Okay.
Got it.
One other question, Liam, is from Pratyush asking, is the model basically PIOPs? So I think polynomial interactive oracle proofs, or is that right? I think it's what a PIOP stands for, with the ability to query a degree 2 product of the oracle polynomial. It's in the chat too. The way I read it was confusing.
Okay, hold on. I'll try and answer.
Yeah, I can also just ask it directly. So basically, so you said you're able to, I guess, you're using the pairings to take, I guess, a product of the polynomials, right? So is the model that are you sort of querying, like if I have two oracles sent by the prover P and Q, if I want to query the product, I can, get the evaluations of both and, get the product. But I can also, if I have a commitment to P in G1 and a commitment to Q in G2, then I can try to, check an identity, for example, by computing the pairing between the commitment to P and Q. Does that make sense?
Yes. That will be key, right? Because evaluating P would take D time because it's degree D. So the pairing allows us to, like you say, take the product of two polynomials without querying them directly.
Yeah, that was actually what I was trying to get at with my previous question, because I was wondering what the efficiency of operating on these polynomials was. That answers it as well.
Okay.
I'll say as a little plug that I tried to formalize this in the lookup paper. So there's this model that Pratyush relates to your question. And the point is, in like the compilation from the abstract PIOP to a real protocol, if you've only done degree 2 checks on certain polynomials, then for those polynomials, you don't need to pay for the time to compute them. Like only the time to compute their commitments.
Okay. Yeah, so on that note, there is also, I think, in the Lunar paper, they explore it there, I believe, in the context, maybe in a similar context, where they also use G1 and G2 KZG commitments to be able to check degree 2 relations without having to actually compute the product. So that might also be something you might want to see if there's any similarities there or ideas there that could be ported over.
Yeah, I mean, I remember taking a look, and I don't remember what my conclusion was, but though I remember still feeling like I need to write down this model.
Yeah, I think they didn't formalize it, like they didn't extract like an information theoretic component out of it, as far as I remember.
So say again which paper that was?
Is this a Lunar paper?
Okay.
I don't know the full name. Lunar, a toolbox for more efficient, universal, and updatable SNARKs. I'll put the link in the chat.
Thank you.
Awesome. Any other questions on this topic, or Leah, are we good to let Liam continue?
Yeah, sorry. Yeah.
No, it's all good. I guess, Liam, go ahead. Keep on rolling.
Yep. So can commit to P in OK time, and then the important property for sparsity for our purposes is that it's linear, right? So P times F, if P is BI sparse, then P times F is BI times F sparse, just by distributing the F multiplication. And you can kind of imagine that this is where the pairing might end up. So some simple examples of what we can use sparse commitments to do is like degree checks. So we want to show P is degree D, but the trusted setup has degree N. We can compute for our basis these X times big N minus D times the BIX, which are of maximum degree. And then we can compute this D value and check that P is no more than degree D. I guess that should probably be a less than or equal to D in the first bullet point. But yeah, so this is a way to check that P is of degree no more than D in O of K time, right? Because P is B sparse. Then the next thing is opening, say, to fixed value. So we want to open P at 0, for example, as part of sum check, say. We can pre-compute the openings of all of the BI at 0. And so, for example, in the case of Lagrange polynomials, these can be computed very efficiently. And then similarly, we can take Z as the F linear combination of these ZI and check that P equals C, just like that. So these are some simple examples that are sort of useful later. Yeah, and then a more complicated example is how we can use these sparse commitments in CQ. So we have a table that in, point-wise encodes a vector, TI should be, and then we want to prove that some value is in the table. And if we have then A, right, is Lagrange sparse. So imagine A has mostly zeros everywhere, except for the places of the table that we're interested in sort of reading. So when we multiply A by the table, it'll sort of pick out those parts of the table, and the 0 will cause the B on the right-hand side to also be 0 at the parts of the table that we're not interested in. So A is Lagrange sparse by construction, but we also know that B is Lagrange sparse because A is mostly 0 on the left-hand side here. And then the interesting part for CQ is that Q is also n-sparse. There's a set of QI values, which are defined there, so that you can write Q as a linear combination of these values by the values of A. So if you were to take like the values of A at the points where it's not 0, and you add up the right-hand side or the left-hand side, and then the B will be those values times TI times the middle term, and then Q will be the same values times the QI added up. Now for the CQ, we can compute these QI values using the FK technique, basically some DFT, FFT stuff over curve points in n log n time, which is pretty cool. And that lets us work with very large tables. And we can compute A of X, B of X, and Q of X all in little n time. So that's independent of the size of the table. And, doesn't make sense to get deep into CQ, but basically you can use this trick to encode the log derivative lookup in, I guess it would be the polynomial A, or yeah, A. And then ultimately you end up just summing over the values. And since A is mostly 0, there's only little n values to sum over. And so we can use the same sort of sum check sparse stuff that I talked about on the previous slide to do that efficiently. So yeah, sparse commitments, very useful. Now we'll move on to the Lynn check problem. So we fix an n by n square matrix M, and given commitments to two vectors, we want to show that M times A equals B. So goal is to do this in O of n group and scalar operations. And so since M is n by n, A and B are both dimension little n. How? So first we'll encode it as polynomials, natural first step. Then we're going to perform this M times A as a product of polynomials using the pairing. And then we'll take advantage of the fact that M is fixed, independent of A and B, to pre-compute quotients for this product. Find sparse basis for all the commitments. So the quotients, for example, would be part of that. And then commit to everything using that basis. And finally, which I won't talk about too much. I think it's sort of clearer maybe to write it using bivariate polynomials, but everything can be done using univariate polynomials. So recall definition of matrix multiplication. M times A is just a linear combination of the columns of M. So we can encode B and the columns as polynomials. And then the matrix equation holds only if this linear combination of polynomials on the left equals B. And so now a matrix is sort of like a vector of vectors, right? It's a two-dimensional object. And we can introduce a new variable and use the same sort of technique to encode the matrix as this bivariate M and have its evaluations at Y, or the roots of unity at Y, be the columns. And so simple code, vector A is a polynomial. Now the matrix equation holds if this sum over the values of the polynomial A times the values of M equals B. Now we can introduce this variable or this polynomial R, which will just be the product. So it's all the terms in this sum, basically. And this, it turns out, is equivalent to R being M times A mod y to the n minus 1, because that holds if and only if both sides are the same at all the roots of unity. And then that is, of course, just equivalent to having the quotient. Okay, so now our matrix equation holds if this R is well formed as the product of M times A mod Q, or mod y to the n minus 1. And then if the sum of R over all the roots of unity gives B, and the degree of R in Y is less than n. And that final point is so that we can use the sum check to just evaluate R at Y equals 0, and then we'll check that it equals B. So this is, fairly straightforward, I think. You're just sort of converting into polynomials. We would like to construct all of these polynomials in O of little n time. So we need to find a basis for each polynomial that is little n sparse. And it's worth noting here that the A and the B aren't super, they're not super surprising that they would be, little n sparse, because they're just encoding vectors of dimension n. The interesting polynomials are R and Q, because they're bivariate polynomials. And so even if X and Y both only have degree n, then there's a potential for n squared terms. So degree checks, pretty straightforward. So this is how we can kind of compute R using a basis of little n polynomials. So remember that R, when you evaluate it at Y being a root of unity, should give A sub I times C sub I of X. And here, that's sort of exactly what we have on the right-hand side, because when we evaluate the Lagrange polynomial at different roots of unity, it's 0, except for when the root of unity is raised to the ith power. And so evaluating at a particular Y, you would get the correct thing on the right-hand side. And notice that there's only little n of these commitments that we need in order to commit to R. And
sorry, one thing, CI here, I think are the rows of M, right? The polynomials committing the rows of M.
I think they're supposed to be columns. I do sometimes mess up the indexing with rows and columns, but yeah, here, so the CI come from these CI, and so
okay,
and then they go here, and so yes, the CI would be the columns of M, I believe.
Perfect.
Yeah, and so the CI can all be pre-computed because we know M in advance. And since the CI can all be pre-computed, you can pre-compute all of this, and then during proving, you only have to take these little n scalar multiplications. Then the sum check over the values of y, like we said, can be done by having the openings of this value at 0. In the univariate case, that's a little bit more complicated, but not too much. I think it makes sense to think of it more like this, like sort of having an independent variable and opening it at 0. But each of these openings at 0 is just pre-computable, like we talked about in the much earlier slide. And so once again, computing the KZG opening at 0 can be done in little n scalar multiplications. And so that just leaves the quotient. And so how will we do the quotient?
Quick question
Yes.
from the chat. Do we only actually need the CI, not the original M? And the context is it might be useful if the matrix is private. Question from Dara.
Do we only need the CI?
So we are using M of XY there. So
yeah. The way this ultimately will go is the verifier will have a commitment to M, and this, well, I guess this would end up being actually more like this expression, be a pairing of the commitment A and then a commitment to M. So I think in principle, it should work for private matrices M, yes, private to the verifier.
that sounds useful.
Yeah.
Go
on. Okay, so quotient, I'm just looking at this. I'm trying to make sure that it's correct. I think it's fine. Okay, so this is very similar to the original CQ technique. And so in CQ, you'd have your table here, and you'd be multiplying it by Lagrange Lagrange polynomials. And then you'd have the values of the table here, and they would also be multiplied by Lagrange polynomials, and then you have your quotient. But in this case, instead of having scalar values, they're polynomials. So the evaluation of M at omega to the I will be CI. And so this expression holds mod y to the n minus 1. And then there's some Q value that exists only for this expression for each I. And if we have these QI, then we can take the sum over the AI values of these QI to get a commitment to the quotient polynomial. And so, yeah, this is M times A. So if we were to sum up all of these over the values of I, this equation would be like multiplied by A times I, and then we'd sum it. So then A times I times L sub I of a Y will be A of Y. And then we have M of X. And then over here, we end up with the AI times CIX times LIY, and that will give us exactly R. And so, yeah, summing all of these equations over the AI will make this be R, will make this be M times A, and then this become Q, basically by definition, right? Because this is how we define Q, as R equals M times A of this times Q. So that's how we compute the quotient in little n time. We just need commitments to these QI. Now, these QI don't depend on A or B. They depend only on the matrix M. So we can pre-compute them, and yeah, that's what we want. It's our sparse basis. It's sort of sparse in the set of polynomials of degree n in x and y. So there's n squared terms, like I said before. So to clean this up a little bit and make it into the paper version, we prefer to use a univariate trusted setup rather than a bivariate trusted setup. That's not a problem. We can just substitute x to the n for y, And everything pretty much works. I mean, it's, you know, worth checking, but it's sort of makes sense, right? Because the y only ranges over n powers, and so replacing it with x to the n means that, so this, say, being a polynomial in x and y becomes a polynomial in x and x to the n, so it's a polynomial of degree sort of n squared. And then we prefer to accept our input via polynomial in x. So after we make this substitution for y equals x to the n, this polynomial a, which is a polynomial in y, will be like a polynomial in x to the n. And so if you, for example, wanted to chain this protocol to like multiply matrices in sequence or something like this, you'd need the input and output to be sort of have the same structure. And so this is very straightforward. We just can check that a of some random value equals f of that random value raised to the n, because y equals x to the n. I think that's right. Yeah, and yeah, and so at a random point, and these are both just polynomials of degree n, so this can be checked in a little n time. And that's it. That's all we need to do. Yes?
So why is x to the n? Should it not be a of a to the n equals? Sorry, alpha, a of alpha to the n is f of alpha. Or have I got that?
I was just wondering the same thing. I think this is right because so like a will be after we make this substitution, it will only have terms of degree divisible by n.
Oh, sorry. Yeah.
And yeah, so yeah. Yep. Yep. And so I guess any questions, or that's mostly the protocol. From here, I just had like future work stuff, potential improvements that I'm interested in working on. Okay.
Also, I guess, Ariel, if you have any commentary that, you know, since I know you're a co-author, I mean, feel free and share if you have any commentary as well. Otherwise, we can let Liam proceed with the rest.
Yeah, no comments.
Nailed it, Liam. All right.
Yeah, absolutely.
All right, keep on rolling then.
So stuff I would like to improve upon or see improved upon. One natural generalization is moving beyond just using the roots of unity. I mean, obviously, roots of unity are super convenient to work with, but they don't always exist. And yeah, being able to not depend on them would be great. And I'm fairly confident this is doable. The only significant dependency on the roots of unity is the Aurora sum check, evaluating at 0. And there are ways to get around that. And then the O of n log n. And so if, say, you used cosets of roots of unity, you'd have something like O of n times m times log n plus log m squared, or something like that. But that would make it, I think, more practical over a larger class of curves and larger, sets of matrices. And that's also
because you don't necessarily have a set of roots of unity of the right size.
Right.
Okay.
And also this in the context of CQ. So for lookup arguments, if you want, say, a lookup table size 2 to the 32, and you don't have 2 to the 32 roots of unity or some product of values that's acceptably close to that, using larger vanishing sets would be cool. And also,
sorry, you say that the only thing where you need roots of unity is for the sum check?
The sum check and the O of n log n, like FFT algorithms, just like for setup and stuff. I believe so. Yeah. Most everything else,
Check
like
you can do it without roots of unities.
what's that?
Like the sum check, you can do it without the root of unity set.
Yeah. Yeah. So
Like the inner product. So that should be easy.
yeah, I think so. I haven't like worked it all out, but it seems like it should work.
I can send you a reference. But so for the FFTs, yeah, there you are.
Yeah.
So,
I am interested in using ECFFT potentially for using the set of whatever, like x coordinates of the two power subgroup, and that I believe has I know it has n log n for certain algorithms, and I think those are sufficient for doing generalizing these cqlin protocols to that set of vanishing polynomials.
Yeah, I think the question there is, does the asymptotic improvement for ECFFT outweigh the constant factor slowdown?
Yeah, I don't know. I think it'd be cool to experiment though.
Yeah.
Yeah, and so then just generally reduce work prover size trade-offs. As I've described it here, it's all sort of more abstract algebraic equations of degree 2. And so there's lots of ways one can kind of play around with trying to put them into pairings and commitments to trade off proof size, prover work, etc., that kind of stuff. So that's maybe worth exploring. And then the big interesting one is improving the setup time or trusted setup size for sparse matrices. So right now, the trusted setup has to be n squared, right? And the setup time is also n squared. But if we wanted to use this for like an R1CS matrix that was very sparse, that would be undesirable. We would prefer if it only required a trusted setup that is linear in the sparsity, and the setup time that only depends on the sparsity. So interested to see if some of the techniques here or other stuff or just future work in general is able to improve on that while still retaining linear prover time only in the dimension of the vector. Yeah, and then just other applications of precomputations and pairings. I didn't have anything in particular in mind, but yeah, interested to work on that more. Yep, and that's it.
Cool.
Awesome. Thanks, Liam. I know we've been this has been more a free form discussion, but I guess at this point, at the end here, does anyone have any lingering questions or comments on the protocol that Liam just presented?
Oh, yeah. So I
knew you had comments, Ariel.
Yeah. Yeah, I had actually I did right. I lied. I had a comment, but I wanted to say it well, so I needed a few minutes to. So Liam, if you could go back to the slide where you check that f is like an n or a is an nth power, was towards the end. Just the final touches. So yeah, so just a cute little technical point. So here we have this polynomial capital A that is a polynomial of nth powers, but of degree roughly n squared. And just a simple, nice technical point that you can see in the paper is that if you have a polynomial that's of nth powers of degree n squared, and you want to open it at a point that is wait, actually now I'm seeing that even though I thought of it, I'm saying it wrong. Okay, so yeah, you can open a polynomial of nth powers of degree n squared at a random point alpha in time O of n. So that's just a little cute technical point, right? Because if you did it totally straightforward, the KZG proof for A the prover would pay n squared at this point.
Is that the technique stated in Claymore, or is a
Is it
different one?
stated where in Claymore?
Claymore.
I don't
Let
know.
me
So
look.
we did yeah, we did it in cqlin, but that's you're saying maybe they do something similar.
I mean, I haven't.
Arantxa, and I'm going to ask this mainly for the benefit of anyone who views the video. Can you provide like a little context on that question?
No, I'm just asking if the technique to open this KZG polynomial that has, so yeah, direct and Claymore, I think. If it is the same technique of you introduce a new one.
It's a new one. It's claim
Okay.
4.3 in the cqlin paper.
Okay.
It's a simple observation.
Cool, and I'll post the links to these papers in the video description. Was there more you wanted to add there, Ariel, or?
No, that was it.
Cool.
I did have one question. So is there a way to sort of extend this to work for Lynn eval instead of just Lynn check?
What
I
is
guess for context, so I guess Ariel knows about Lynn eval. Maybe the only other person in the chat who knows about Lynn eval. But Lynn eval basic. So Lynn check says, okay, I have this vector, this polynomial b, which encodes the product of m times a, right? And I want to check that m times a equals b. And the idea then sort of you can go ahead and use b wherever you would want, like say to perform your Hadamard check or whatever, right? Another way to do it is that instead of materializing b, you sort of directly answer queries to b by making queries to sort of m times a. And Lynn eval is a protocol for sort of evaluating this linear combination at the points of your choice. So Lynn eval, like you can construct it like in a similar way to in sort of the sparse polynomial or with complexity that grows with the number of non-zero entries in a similar way to like how we do it for Marlin. So I was wondering if sort of these techniques would also, you know, similarly extend to Lynn eval instead of Lynn check.
I don't know. Maybe. Evaluating with the sparser polynomials can sometimes be tricky because well, like you can't you know, evaluate the polynomial directly. Like for example, m would be too large, but I think it's plausible. I don't know, Ariel, what do you think?
I don't know. It's a good question. I have to think about it, right? It's sort of like the question, can we run the protocol without a commitment to B? Yeah, I don't know. Good question to think about.
Okay, I have a question. Suppose you're trying to use this in a snark or some larger protocol that you want to be zero knowledge. Would you just use blinded KZG commitments, or would you pad the matrix with random values, or how would you go about that?
I'm not sure. The paper doesn't do zero knowledge. It's only...
yeah. I mean, it's focused on a component rather than a full snark, so that's quite reasonable. Yeah,
I think it should be possible to do it similarly to how we do it in Marlin, where sort of your b and a polynomials, you sort of randomize them by adding in an appropriate multiple, like a random multiple of the vanishing polynomial. Though I don't know if that'll like screw up any of the sparsity techniques or not. You can also do it by sort of making the m, like adding a dummy row at the end of m or something along those lines. That's a different way.
Right.
By the way, a separate question. So if the matrix has some structure, say it's like, like say it's a Merkle tree matrix, right? So there's like the same hash function copied over and over again. Do you think in that case, there's ways to cut down on the pre-processing time? Because it's not only is the matrix sparse, but it's very highly structured. So like in the, I guess, this problem is already solved by succinct Aurora. So but basically there's this paper, it's like a follow-up to the Aurora paper, which has a succinct Lynn check for these succinct matrices, but it has this unfortunate dependence on the sort of, like your field needs to have two different smooth subgroups. So like say 3 to the m and 2 to the n or something like that.
Sure.
I was wondering if, using these techniques, maybe you can get rid of that dependence. I don't know.
Interesting. Yeah, I don't know. That sounds interesting. I'll have to look at that. Do you know why they need the two different smooth subgroups?
Essentially, sort of they decompose the structured matrix into like, so let's say if you had a Merkle tree matrix, right? It's like a staircase matrix of the same hash function submatrix repeated again and again. So they sort of decompose this into like a small dense matrix, which is the hash function matrix, and like one very structured matrix, basically close to like the identity matrix or something like that. And then to do this decomposition efficiently, they basically apply like the Chinese remainder theorem to, so they encode the matrix in the full subgroup, so 3 to the m times 2 to the n, and then to go down to like the subgroups corresponding to the two decomposed matrices, you need to apply the Chinese remainder theorem. It's a bit technical. I probably didn't do a great job of explaining why they need that requirement, but yeah, maybe if you could take advantage of some structure in this setting. It's essentially like saying you have like a structured table in some sense.
Mm-hmm. Yeah, I think that would be interesting to look into. I wonder if that kind of needing the two independent subgroups, if you could use like the what is it, like the full torsion of an elliptic curve, like if with EC FFT, if you had an elliptic curve with two independent subgroups of order 2 to the n, or if they need to be co-prime, maybe that wouldn't work.
I think the problem there is sort of usually then your arithmetic circuit would be over a ring as opposed to a field, and then you run into some other issues. Maybe.
Did I get the right paper? That's a guess based on the authors and
yeah, that's the right one. Yeah.
Okay, thanks.
Thanks for pasting it. It's a bit of a opaque paper to go through. It's written very abstractly, but sort of when you drill down and like make everything concrete, the core technique is this Chinese remainder theorem decomposition.
Awesome. Any last questions for Liam or Ariel, I guess? Okay, awesome.
I have another question. Have you tried to plug this into any existing sort of larger protocols?
No, I have not implemented anything.
Okay. Simple answer.
Well, hopefully that leaves a lot of room for potentially other exciting work. So thank you very much, Liam, for presenting. Thank you, Liam and Ariel, for writing this, putting this together. And thank you everyone for being here and contributing to what I think was a great conversation.